I don't have a worksheet for you guys yet. It should be here in a few minutes. I do have some extra practice stuff for balancing equations. We did kind of part of it on Friday. It's from this POGO activity. It then ties it into climate change. So before you guys leave, maybe it's worth grabbing a copy of this. So for now, let's start off kind of thinking off of some of the equations that we worked on. There we go. Thanks, love. Do you mind passing just a few down each aisle? That'd be great. We talked a lot about combustion of octane last class, so let's continue down that vein. We burn 30 grams of each, which is going to be our limiting reagent. Everyone have a worksheet? Anyone need a worksheet? Who doesn't have a worksheet? All right. Shouldn't this just be a simple yes or no question? Shouldn't we just be able to click in? There's no limiting reagent, right? Why is that a faulty statement? What is that assumption that I would be making if I said there's no limiting reagent? There's the same mass of both.
The moles of both are equal.
Possibly. So what are we comparing when we say limiting reagent?
How much it takes.
How much it takes, how much it makes, a couple different ways of saying it. So to do this sort of a calculation, we have to spend a bit more time. All right? So there's two misconceptions that you can easily fall into when you're starting to learn to calculate limiting reagent. One is that if you have an equal amount of both in mass, it means that you don't have limiting reagent. The second one is if we had 2 grams of octane and 25 grams of oxygen, neither one are limiting. What's the problem there? You get a hand raise? What's the problem if I say 2 grams of octane and 25 grams of oxygen, we would not have a limiting reagent?
The coefficients are how many moles, not grams.
Great, so the coefficients are about moles, which is a measurement of what kind of quantity?
The number of actual molecules there are.
So the number of them. So remember last class we had over here that we're talking about, are we talking about mass? Are we talking about volume? Are we talking about length? Are we talking about quantity or number of them? So stoichiometric coefficients are not dealing with the mass ratio. They're dealing with how many of them are needed to react with each other. So hopefully if we're visualizing the molecule, in order for a reaction to proceed forward, we need to have 2 octanes and a whole bunch of oxygen, specifically 25 to make that reaction go. That ratio always has to hold true. So in this one, I don't have the answers popping up on my clicker base. I think we're still doing calculations. Raise your hand if you want another 30 seconds a minute to do calculations. All right, keep doing calculations. If you finish, check with people around you. If you're not quite sure how to do these calculations, ask around, or you can raise your hand and I'll be happy to come work.
Right, so
So let's start kind of working through this together. Did everyone see that homework is due tonight? And the quiz. Yes. So if you've already completed both and you're comfortable with it, that's great. If not, the homework is due tonight. So if you guys are working through a homework set and you feel like you would really like to have it due the next day, which is what 3 students emailed me at 11 o'clock last night. So that's fair, and I'm willing to flex on that. But please don't email me at 11 o'clock at night on the night it's due. Like, if you're working on a Friday, and you're like, this is really far from what I think we can do, I got home from a road trip last night at 11:27 p.m., and I got these emails, and I was like, oh, like, I wish I'd had these emails earlier today. Then I could have actually either guided you guys to some resources or extended the homework, one of the two. And then people that were working on it for hours and hours last night, we could have had a dialogue.
So does that mean if you fudged up on the homework last night trying to get it done, just read some,
So did you use up all your attempts? Is that what you mean? How many attempts can you get?
9.
Okay, so if you use up all 9 attempts, you should post the discussions and let me know before then for the future. But so if you ran out of attempts, I might be able to undo that. I'm not sure, and let you continue. But the homework is due tonight, so I moved the due date to today. I'm not sure what that means. Oh, the quiz. You're talking about the quiz. Yeah, the quiz was due tonight anyway, regardless.
The homework itself had a time.
Okay, let's talk about this after class logistics, okay? I want to help figure it out. I'm not trying to downplay that, but I was unaware that the homework had a time limit, and so I need you guys to help me figure that out, all right? All right. So for this problem, this is similar concept to what you guys are doing in your homework. So let me hear, you might not know how to do the whole problem. We want to know how to start it. I want to hear from different voices throughout the day today. By volunteering what you're thinking, it helps us hear from voices that don't always know exactly how to do it. So I really encourage you to speak up and share your thoughts on kind of how to get started, or if you have an idea of how to do a step. I want to hear from every person in this class, ideally. So can I hear from someone who has an idea of how we start moving forward? Savannah?
I set it up so as to do a gram-to-gram conversion of octane to CO2 and then O2 to CO2.
Okay, when you say a conversion between octane and CO2 and oxygen and CO2, what do you mean? What units? So let's think about in those terms.
So like I did 30 grams of octane, and then I did the conversion factors to find how many grams would be in the resultant CO2.
How many grams we'd make, of CO2. Great. So there's 6 or 7 different ways we can answer this question. The way that Savannah's talking about is if we didn't have a limiting reagent for oxygen, how much CO2, or choose one product, doesn't matter. How much of one of your products could you make if we used all of reactant A, octane in this case? Let's try to do the same thing. If we used up all of the oxygen, what's the most we could possibly make in terms of CO2? How do we use that information then to determine which is the limiting reagent?
Well, the one you make the least.
Say again?
The one that makes the least amount of.
The one that could make the least. Yeah. Okay, so that's one way to do it. So do you guys want to write that out? All right, so let's go ahead and how do we do the calculation, Savannah? I'm going to try to get out of the way and draw at the bottom of the board.
First I started out with 30 grams of octane over 1, multiplied by the molar mass, which is 114.23 grams of octane under 1 mole.
Oh, so flip.
Yeah.
And 1 mole would be on the top then?
Yes.
And what am I missing?
Under it would be the molar mass, which is, I got 114.23.
Okay, we're still missing one thing. What are we missing?
1 mole of octane.
Okay, and here's where we have to be extremely specific, and this is why we've been doing dimensional analysis before. I tried to say over and over, like, let's put every single part of every unit in there, is because we're going to be dealing with 1 mole of octane, we're going to be dealing with 1 mole of oxygen, we're going to be dealing with moles of carbon dioxide and water. So all of those, mole doesn't help, right? We need mole of octane. Great. So what do we do in this conversion factor? Can someone say in a sentence like we did last class? What are we converting from and to? Let's take a try. Say it in your head and then raise your hand if I can hear someone else. Kevin?
Mass to quantity.
So say the whole thing. So we're converting from
Grams of octane to moles of octane.
right, and so I would kind of combine those two statements. We're converting from the mass in grams of octane to the number of them, the quantity, in moles. Great. So every time we do a calculation, I want to have you guys say that sentence. All right, and then Savannah, what was your next conversion you did?
My next conversion was 16 moles of CO2 over 2 moles of octane.
Okay, and so could someone use a sentence to say what we're doing there? Matthew?
We're converting from how many moles of octane in the reagent to how many moles of CO2 are produced.
Fantastic. I love it that you didn't just say moles of octane to moles of CO2. You specified moles of our reactant to moles of our product, and you even put them in more context than normal. Great. All right, so now if we stopped our calculations, we know how many moles of CO2 we could produce from 30 grams of octane. So we could stop here, actually, to answer this question. That would be fine. But do you want to say the last step that you did? You found the grams as well, you said?
Yes, I did 44.009 grams of CO2 over 1 mole of CO2.
Okay, and can I have one more person say in a sentence what that conversion factor is doing? What is the sentence that describes that last conversion? Amber?
We're converting from the quantity of in moles to the mass of grams.
Great. All right, so we have 3 conversion factors we used. We ended up saying, if I used up all of my octane, how many grams of CO2 did I produce? And as I mentioned just a second ago, we can actually stop this calculation at how many moles of CO2 would I produce, and that will help us answer the limiting reagent question. The last one is, I might also ask you, how many grams of CO2 can you produce at most? As you might have looked ahead, that's one of the questions that's down there. Okay, so what is our answer for this?
92.464 grams of CO2.
Okay, we can produce 92.464 grams at most if we use up all of our octane. And then if we were to do the same calculation for our O2, what's different? Would we use, obviously we're going to start with 30 grams of O2 out here. I'm going to change the color. Is this going to be the same conversion factor?
Yeah.
All right, so that is going to be, what's that conversion factor going to be? Is 1 mole of O2. All right, so the mass of each oxygen molecule is different. And then, do we use the same conversion factor here?
No.
Natalie, what do we use next?
I did 16 moles of CO2 over 25 moles of O2.
Okay, and can you put that in a sentence? What is this conversion factor doing?
Comparing the number of moles of CO2 produced to the number of moles of O2 in the reaction.
Yeah, and I might say the other order. So we would, because our last calculation ended with the moles of O2 that we're starting with, so we're converting from the number of moles of O2, which is a quantity, to the number of moles of CO2 produced. So kind of going left to right in that flow. Okay, so if we stopped our calculation here, we could answer our question. If we stopped our calculation here as well, we could say which one produces fewer, is capable of producing fewer moles of CO2. If we wanted to go all the way, though, and we wanted to find the grams, what would our last conversion be, Dawson?
The 44.009 grams of CO2 over 1 mole of CO2.
Okay, and does anyone have the calculation for what that actually comes out to?
26.406.
Grams of CO2. Okay, so can you guys answer this question now? Yes, no, yes? Eric, can you tell me how we can use these 2 numbers to answer this question?
Should be fairly obvious. 30 grams of oxygen is going to produce 26 grams of carbon dioxide.
As opposed to?
92.
Great. And so I want you thinking about what these numbers mean. That if we used up all the oxygen and we had an unlimited amount of octane, we'd run out by the time we made 26 grams of CO2. If we had an unlimited amount of oxygen and we only ran out of octane first, we would be able to make 92 grams. And so looking at these 2, the one that we're going to run out of first, stops making product before we get through the reaction, is going to be oxygen in this case.
Would it not, can you just hypothetically look at it simplistically? It takes 2 octane and 25 oxygen, so you know you need a lot more oxygen?
Absolutely, if they weigh the same. But let's say, what's that?
You did put them the same, 30 grams, 30 grams.
No. That's how much you have, not how much they weigh.
Okay, alright.
So this throws a wrench in that. It's like saying, I need to make cars, right? I have 7 billion bolts, and I have 42 engines. They might weigh the same, right? But one of them is going to run out way before the other. So the weight of them is really important to think about when you're doing that kind of work. So what we want to do, the first thing, I was talking to a couple people back there, kind of a simplistic way to do this is just to do this first step, and then look at how many moles of each of them we have. And then you might be able to say, oh, well, I have 7,000 of one of them, and I have 2 of the other. Even if the molar ratio is 2 to 25, we're going to have a pretty obvious answer. Okay? So what are some other ways that you answer this question? Did anyone do different calculations to answer this question? No? Everyone did it Savannah's way? Ruby?
I stopped at the second step like you said.
Okay, so if we stop at the second step, what did you end up with?
There were 0.94 moles of oxygen and 0.26 moles of octane.
0.26 moles of octane.
And then I saw that the ratio was not 2 to 25. It's like 1.
Okay, so what would it look like if we had a 2 to 25 ratio? You don't need to do the numbers. Which one of them would be a lot bigger?
Oxygen.
Okay, we would have a lot more oxygen. We'd have 12 times more, over 10 times. Okay, so in chemistry, to save yourself time, if you can go to the nearest rounding option, so there's 12.5 times more O2 than octane, it's about 10, right? If you can rough the answer. So that means that we would have to have 2.6 or more moles of oxygen to use up all the octane. See what I'm doing there? So just as rough as you can, we can easily say, well, there's about 4 times as much. So that's not 25 times as much, so it's not going to be enough to use up all of our octane. See where I'm going there? So as many shortcuts as you can do to do what Josh was talking about, but we need to do it in terms of moles and not in terms of mass. All right, what are some other ways? Did anyone do a different calculation? You want to see my favorite? Yeah. That's what I heard. I heard you guys really excited.
Is it shorter?
It doesn't answer necessarily the same questions. So Savannah answered, how much CO2 can we possibly produce? That's already built into that calculation. So that's wonderful for that reason. The way that I do this is I say, if I were to use up all of my octane, how much oxygen would I need? So try to write that out. If I was to use up all of my octane, how much oxygen would I need in grams? You guys know how to start that calculation? Go ahead and try that calculation. I'll work through it in a second. I want you to try it on your own first. One more time. If we're going to use up all of our 30 grams of octane, how much oxygen would we consume? And this does answer another question that I have, so it's still valuable. Raise your hand if you'd like me to come and give you a nudge. So this is more of a okay. And then you find so what you want to be careful of is this. It's the same ratio. So technically it's okay. You should always use the 1. So this should be 1 mole. Because 1 mole is 2. I get the no. So it's actually
Excess
Like without going over.
So now you have the number of moles of octane. What do you do with that? How do you use that to determine how many moles of oxygen you need? Comparing, it's always about comparison. It's not using oxygen, it's comparing what to oxygen. All right, so let's take a look. So can I have a volunteer, someone who gave it a shot? Maybe you're not 100%, but you want to try to share your work. Avery?
So I started with the 30 grams of octane, put it over 1, and then multiplied that by the whole octane over the mass, so there's 114.22852. Then I multiplied.
Pause. Always, I saw a lot of people do it. They just say grams in the bottom. Maybe you have it on your paper, which is cool. But as long as saying moles of octane, we have to say grams of octane, because there's going to be grams all over the place, and we need to be really specific that it's grams of octane. So what is this calculation doing? What are we doing with this calculation?
We're going to put it in the moles of octane that we have.
Great, so we're converting the mass of octane in grams to the number of octane molecules in moles. Okay? And then what?
And we multiply by 25 moles of oxygen over the 2 moles of octane.
Okay, so can someone put in a sentence what we just did with this conversion? Logan. So what is this conversion right here doing?
Telling you how many moles of oxygen is used in the balanced equation that we use. It's like how much oxygen we use per octane.
Yes. All right, so I really like what I'm hearing from a number of students in class today. It's not just saying it's converting octane to oxygen. We're not converting octane to oxygen. That's not what's happening, right?
You can't do that.
We're saying how much oxygen do we need to consume this amount of octane. And the ratio is always going to be the same. So if we stopped our calculations now, we would know how many moles of oxygen were used in this reaction.
And then the last one I did was I took the grams of oxygen, which is 31.9988. Sure. And then put that over 1 mole of oxygen.
Okay, and what numeric value did you find?
110 if you do it 6 days, but it's 105 actually. Because you do 2 6 6 or 1 6
Technically that's 1 sig fig. Let's not get into that right now because this is a terrible question I wrote on the fly this morning. Okay, so are there any units on this?
grams of oxygen.
Okay, turn to your neighbor. I want you to put into a sentence what that number means. 110 grams of oxygen. What does that number mean in the relation to this calculation? Why do we do it? What does it tell us?
If we consume 30 grams of octane, it would require we need 110 grams to react to full octane.
Yeah, no, I didn't like that. Would that be okay? Do you want Professor, I have my
As long as you calculate mole mass and stuff right.
She was like, I'm thinking this plastic to just like go to everything that they're wanting to do. So it's time to my
All right, is there any brave soul who has not spoken yet today, maybe not even this semester, that wants to try to put in a sentence how we use this 110 grams to answer this question? Anyone who's been quiet throughout the semester who wants to try to describe the relationship between this final answer and we started with. All right, Kayla. So it was rounded for sig figs, but actually I would argue that each of those are 1 sig fig, so it'd be 1 times 10 to the second, 10 to the third, 10 to the second, yeah. Anyway, so what do you, how does this relate to the answer? Do you want to?
Is this the one where you ask for the excess of O2?
No, we're still asking which is the limiting reagent. And so how does this question help us answer, how does this number help us answer that? Joey?
Well, it takes 110 grams of O2 to completely burn through 30 grams of octane. And if we look at the problem, we don't have 110 grams of O2. So that's limited.
Fantastic. All right, so it's all about comparing what we would need to what we actually have. In this case, we don't have 110 grams, we only have 30. That means we're going to use up all that oxygen. So then this doesn't quite answer question number 4. So question number 4 asks how much of the... So our limiting reagent is oxygen, right? So that question is actually wrong. We would not have any oxygen left because we used all of it. So let's go ahead and ask the question that's on number 4 the other way around. How much of our excess reagent do we have left? Since we're on this thread, let's keep going. So the question now is how much of our excess do we have left? And I think I can actually pull that slide up. All right, so the question's up on clicker. I want you to work through this question and submit your answer. I modified the question for number 4, so it actually makes sense. Please raise your hand if you have any questions, if you want some help when I'm moving forward with this.
I don't know, but that's
Well, technically it's only one because it's not a dot. Okay, I mean, I'm working on it a lot, and I'm still kind of missing some pieces. So I know you should
Okay, going into Friday, I got 3. Going into, I'm gonna tell you all these numbers, just so you can see how much it's left and left. Going into Friday, I got 3. Saturday, I got 5. And then I was up to 3. Going into Sunday, I got 52, woke up to my records here, and then I got another 2. Because then I had to take a little breakfast, and then last night I got. That's how much I normally sleep one night through one.
What'd you get?
Okay, but I'm still. What did you have to round here once you get this one? Did you get 2.4 or Oh shoot, I think I did this number, give me another second.
Oh, okay, sure. They're not in this building. They have to go to the science. I'm sorry.
So I see a couple hands raised. Hopefully working through this. Is it about working through the problems? Okay. So let's go ahead and start working through it, and let's see if we can kind of get on the same page for how this all comes together. So if we're trying to answer this question, how much octane will be left over? Can I get a volunteer to share how we'd start these calculations? Angel? Well, how much? Oh, 31 point, sorry. I thought I heard 39, sorry. We're going to do 32.00 grams of O2. Yep. Okay. So what does that conversion do?
So that converts from in grams of oxygen to the quantity of, to the quantity of oxygen in moles.
Great. And so now, once we've done this conversion, now we can use a stoichiometric relationship. Now we know we can compare very easily between them. So fantastic. All right, and then once you have the quantity in moles of oxygen that we start with, what do you do next?
And then I convert from quantity of moles to the ratio, did I say that? Which is 2 moles of octane over 25 moles of oxygen. Then I convert from the ratio to the grams of octane.
So if we had stopped after this last calculation, what are we actually finding? What is the value of, not numerically, what is this telling us?
Moles of octane.
How many moles of octane we would need to use up all the 30 grams of oxygen. Okay? And so the final step you said was 1 mole of octane weighs
114.22 grams. And I got 8.57 grams of octane. And then I subtracted that from the 30 grams of oxygen.
So wait, let's put in a sentence first. So what is this 8.57 grams of octane?
That's telling us how much we would use.
Great. So if we use up all the 30 grams of oxygen, this is how much octane we'd use. Do we have more than that? We have way more than that. And so we could have done the calculation I showed you a minute ago where I did the calculation from octane, how much oxygen would we need. This is the other way to do that. Either way, if you start with oxygen or octane, you can determine your limiting reagent by saying, what does this number mean? How does it compare to how much we have, like Joey said. Okay, so then if we have more than this, the question is, well, how much is left over? What's the excess? And how did you find that?
So I subtracted 8.57 from 30 grams and got 21.43 grams of octane in excess.
Great. Questions? Eric?
Round off for sig figs.
Yeah, so this was a terribly worded question on my part. So if I was to ask this and I wanted you guys to pay attention to sig figs, what I should have done is put 30 point, which would have been 2 sig figs, or 30.0 would have been 3 sig figs, and then we could have determined our answers off of this. One really, really, really important distinction, though, is a lot of people would say, well, then does this become 8 or 9 when you do subtraction? And that's not appropriate at all. You would never round your answer until you got to the very end. So you would do your calculations up to here, and then you would note this should be 2 sig figs or 3 sig figs, whatever it is. So that means that significant, if it's 3 sig figs, let's say, all 3 are significant. That means that over here, if we were certain at the ones place, this is certain to the hundreds place, we would round to the ones place. So remember, there's 2 different sets of rules. You need to remember how many sig figs this would be if we reported the answer, but you use everything that came out of your calculator when you do the calculation, but it just determines how many, what you report for your final answer. All right, we've got 5 minutes left of class. I think we've done most of the things I wanted to, though. There, Poggle number 30 in your in the PDF that I posted online. This is we have a couple questions here borrowed from that, but that is a really, really, really good resource for you guys to practice limiting reagents. And then I'm going to put these, actually during the next time I walk around, I'm going to put these in the back. This is a good resource for practicing just figuring out how much product you can make from each of the reactants, and it ties it back to climate change. So I didn't print out Poggle Activity 30 because that is a PDF online you guys already have, but I do have printouts of this. So, let's go ahead and, this question is towards the bottom, right? Question number 5. I want you to try to answer this question. I want you to try to do it showing dimensional analysis.
I think I did it right.
Do you want us to type in what can be produced from each calculation, or just the one, just the resultant of the limiting?
Yeah, so this has two questions built into it. What is the limiting reagent, and then what's the least we can produce, which means you use a limiting reagent. All right, I'm looking at my clock. Take another 20 or 30 seconds. Make sure you have it laid out. I'm not as worried about the calculations in your calculator. All right. Can I have two volunteers to give me, well, either one volunteer to tell me how they did this, or two volunteers if there's two different parts of it. Josh, how'd you work this? So use a stoichiometric. So first you converted from the mass of NO to how many moles it is, and then how many moles of NO to how many moles of NO2 you can produce. And then we said the mass. So what was your final step?
I did 46 grams of NO2 over 1 mole of NO2.
And what did you find for your mass? Okay, and if you did the same thing starting with your other reactant of O2, what would you find? Your final answer for that.
I didn't convert that one all the way. It was 200 something.
Trip G?
I got 143.781.
That's what I got.
Okay, so based on this alone, which one's our limiting reactant? Nitrogen monoxide. Last question is, hasn't hit 50 yet. Let's say that we only made 47.3 grams of NO2. What's our percent yield? Okay, so I'm hearing a lot of people recite the equation. Did we make as much as we could have? No! Okay, we could have made up to 61.3 with the limiting reagent before you run out, but we didn't. What is this percentage-wise? Is that about half? Is it about 2/3?
It's around 3/4.
It's about 2/3 or 3/4. So I want you to do that mental math in your head first, and then you say, well, we made 47.3 grams. We could have made at most 63. So what is that fraction? 0.77, which is 77%. Okay? You guys have your homework is still due tonight. The quiz is due tonight. If anyone's willing to stay for a minute after class and let me know what you're talking about with the time stuff, I want to figure that out. And if there's something I need to do to reset to make sure that you can actually get to finish your homework, I will try to do that. Make sure to use the POGO activity I handed out as practice. Make sure to use POGO activity 30 in that PDF online as practice as well. Steven, if anyone doesn't have their exams too, I have those. So it just show it was due tonight on the 15th. Let me check one thing. I think I might have an idea.